Hi, everybody. Now we're doing, as I said, part two of my 2.8 video on the curve sketching. First, I just want to say that I am not being endorsed by the Chicago Bulls, nor am I endorsing the Chicago Bulls. I just happen to be wearing this sweatshirt for free. I should pay them. They should pay me for advertising their product, but what can I say? Um, I'm just wearing it for warmth. Now, let me share my screen. I want to go over these are kind of a checklist of things you want to look for when you're doing curve sketching. One, you want to find the domain and the range of the function that you're going to sketch, because that would help a lot if you know where this function is defined and how big it gets and small it gets and so forth. Two, something's going to help you a lot is figure out the X-intercepts and the Y-intercepts. The Y-intercepts are usually super simple. The X-intercepts are sometimes easy, sometimes harder to figure out. And I'm talking about here, when I talk about curve sketching, I'm kind of talking about sketching it, by hand, not with not on Desmos or on any kind of device. Number three, which will help you a lot, is to figure out the asymptotes, the horizontal and the vertical asymptotes. Now, if you notice, if you're very sharp, you may have noticed that I have 5 things listed here, and for the first 3, for items 1, 2, and 3, they're all italics. And the reason I italicize them is because the first 3 things have nothing to do with calculus. They're pure algebra. This is algebra stuff that you learned before you even took this calculus class. The calculus part of this doesn't start until step 4. So on number 4, the thing we're going to look for in our checklist, we're going to look to see where the function is increasing and decreasing, the intervals where it's increasing and decreasing, and we also want to find the relative extrema, meaning the maxes, the mins, and max and mins. And step number 5, the last thing we're going to need to do for our curve sketching is to figure out the concavity and the points of inflection. Concavity is whether it's concave up, concave down, and points of inflections is where the concavity changes. I wanted to point out that in order to find the extrema, you're going to need to find f prime. And in order to, let's see if I could make this a little bit. So we get the fill line. In order to find the points, the concavity and the points of inflection, you're going to need to find f double prime. So the places where it's increasing and decreasing and the extrema, you're going to find with f prime. And you know what we're going to do? Actually, I'm going to put this back. I'm going to do this. Yeah. Okay. Actually, the book, I say relative, but the book uses word local. So I'm going to change, I'm going to use their book. I'm going to use their word. And then I can make this all, that I'm able to make this all 29. There you go. Oh, wow. Still doesn't work well. I'm wasting everybody's time here. And notice also that in finding all these things, we're going to need to find the zeros of f prime, and f double prime, because the x-intercepts are going to be the zeros of f. The local extrema will happen at the zeros of f prime, and the points of inflection happen at the zeros of f double prime. Not every zero of f prime is an extrema, is a max or a min, and not every zero of f double prime is a point of inflection, but the extrema and the point of inflection happen at the zeros. And of course, the intercepts happen at the zeros, and those go hand in hand. Okay, well, let's just do an example now. Now that we figured it, now that we got this little checklist, let's do an example. So we're going to go to, let me switch cameras here, and we're going to go to, here we go. So we're looking now at the function y equals x cubed plus 3x squared minus 9x plus 5. So first, now since this is a polynomial, the domain domain is all real numbers. So the domain is negative infinity to positive infinity. And this looks a little weird. Okay. And since it is a third degree, since it's an odd degree, then the range is also going to be all real numbers. Let me just range is also going to be all real numbers. So negative infinity to positive infinity. And that's domain and range. Now the what was that? I want to I'm in the wrong place now. The next thing I want is the X-intercepts and the Y-intercepts. So to get the Y-intercept is very easy. You just set X equal. So for the Y-intercept, you just set X equal to 0. So Y equals 0 plus 0 minus 0 plus 5. So the Y-intercept equals 5. Or you could say the Y-intercept is 5, or you could say the Y-intercept is the point 0, 5. I've seen it done both ways. For the X-intercept, that's for there, we're gonna have to factor this. So hopefully we could factor this. And let's see if we could factor this and get the zeros. Well, one thing I noticed as far as factoring, and this is an old trick I always did in high school, is that if you add up the coefficients and they add up to 0, because 1 plus 3 minus 9 plus 5 comes out to 0, because that just winds up being 9 minus 9. And if you when that happens, that means x equals 1 is a that means x equals 1 is a 0. Because adding up the coefficients is the same thing as letting x equal 1. Because you get 1 to the third plus 3 times 1 squared minus 9 times 1 plus 5, and that equals 0. So now I could do synthetic division. We have 1, 3, negative 9, and 5. And here we have 1. And bring that down, we have a 1. 1 times 1 is 1. We add, we get 4. 1 times 4 is 4. We add, we get negative 5. 1 times negative 5 is negative 5. And we add, we get 0. That's our remainder. We're very happy about that. That means that that means that y is equal to x minus 1 times x squared minus 4x minus 5. And this is a quadratic, which is easy enough to factor. The factor is x minus 1 times x. That's pardon me, x plus 1 times x minus 5. And before I go any further, I want to correct a little mistake I made. 1 plus 4 minus 5. So that's plus 4 means that's x minus 1 and x plus 5. So y is equal to x minus 1 squared times x plus 5. Now, so the x-intercepts are 1 and negative 5. And we also know from algebra that since this factor is raised to an even power, the function hits the x-axis when x equals 1, but it bounces. Hits it and it bounces. And here it hits it and goes through. meaning to say, let's see, it's gonna like go through here, and it's gonna hit it, but just kind of bounce. So that's gonna be 1, and that's gonna be so just be aware of that when it's an even power. And again, this is algebra. This is not we haven't done a stitch of calculus yet. We have not done a stitch of calculus yet. The next thing is asymptotes. Well, polynomials such as this do not have asymptotes, do not have horizontal or vertical asymptotes. So there is no horizontal asymptote and no vertical asymptote. Noha, and nova. Well, all this, as I said, all this has been algebra, these first three steps. And now finally we're going to go to calculus. So let's get y prime. So we're up to step 4. So I'm just going to number the steps here. That's step 1. That's step 2. That's step 1. That's step 2. Step 3. Now we're up to step 4. We're looking. We need to. We begin step 4 by taking a derivative. So if y is equal to, just to remind us, x cubed plus 3x squared minus 9x plus 5, then y prime is going to be equal to 3x squared plus 6x minus 9. And I could, first of all, just pull out a 3. So it's x squared plus 2x minus 3. And now this easily factors into 3 times x minus 3 times x plus 1. There we go. Oh, sorry. X plus minus 1. Okay. I think today is my. Everyone has their days. Everyone. I wanted to know something. By the way, I could edit out these little mistakes, but I want you to see that people make mistakes. Professors you fix it. And the wonderful thing about math is that if you notice right away, if you don't notice a mistake, then there's going to be a problem. That's a life lesson. Now, we now have our critical numbers here is -3 and +1. So let's let's put this on a little number 1. So let's get some test points here. We'll take I just love making 0 as a test point. I love let's make 2 as a test point, and let's make let's see x plus 3 -4. Let's make -4. Let's make -4 a test point. Okay, so if I have my function y prime, so 3 times -4 squared plus 6 times -4 minus 9. And all I care about is this positive and negative. This is 3 times 16, which is 48, minus 24 minus 9, which is going to be 15, which is positive. Again, I don't care if it's 15 or 16 or 17. I just care if it's positive or negative. It's not the value that matters per se, just the positive negative. Now I'm going to do 0. Well, I just get 0 plus 0 minus 9. So this is -9. So big negative number. And now we're going to plug in x equals 2. So that's 3 times 2 squared plus 6 times 2 minus 9. And that's 12 plus 12 minus 9, which is also 15. I see that my function is positive, negative, positive. So it's going up, it's going down. So again, if I would just do a rough sketch, I'm just putting together what I have now. I already know it's gonna hit it. Well, let's say I know it's gonna hit at -5. It's gonna hit the y-axis at +5, and the x-axis at 1. And I also know that when it hits the x-axis, it's just gonna bounce up. And I know, let's see, what else do I know? Something. Sorry. Now that I think about it, I have to change my drawing here. Again, this drawing is a very quick drawing I did, but I realized I do the because it's supposed to have its max. And here it makes it look like it has at the so let me get rid of this picture. See, that's math. Math is an art. Math is an art, and you take the clues, put it together, and you get your masterpiece. Okay, let's. So I'm going to do again a rough curve at this point. We're going to keep on making this better and better. I'm going to go up like this. Then so it's going to hit it. This is going to be x is -3. And we have a max, a min. So it's increasing. Notice the function is increasing here, decreasing, and then increasing again. Increasing. Oh, yeah. The math really anyway, let's get concavity. And the concavities and that's again, we're going to have to go now to step 5, the second derivative. So let's go to step 5. Well, y double prime is equal to 6x plus 6, which is 6 times x plus 1, which means y double prime of -1 equals 0. So -1, -1 is a 0 of this function. So y double prime. So if we make the number line, that's -1. Let's let 0 be a test point, and let's let -2 be a test point. So 6 times -2 plus 6 is -12 plus 6, which is -6, which is negative. And then 6 times 0 plus 6 is +6, so which is a positive number. So we see it's concave down over here, concave up over here. And since concavity switches, that means -1 is a point of inflection. So we have a POI. So now let's put our little graph together. So it goes this and just taking some of the information we gathered before. Okay, so this is all right. This is concave. And it's increasing. Function is decreasing. It gets very busy. And it's increasing again. And then no horizontal. There's no horizontal asymptote, no vertical asymptote. And the the domain range is all real numbers for both, and we have it all. So we know exactly is the function. Now I'm going to graph this on Desmos, and let's see how our picture stacks up to Desmos. Although one thing we're going to see in Desmos, I actually want to prepare you a little bit. There's one thing which I didn't ask for, and but sometimes you could be asked this. I just asked you the x value for the max and the x value for the min, and the x value for the point of inflection and for the min. I never asked you what the y value was. Like, where exactly is that? Like, how high up is it? Well, this is easy. I know it's 0. But where where exactly is the point of inflection? Where exactly is the max? Again, it gives us a better, more accurate drawing. So um, let's do that. So what I want to do is I'm going to take negative and look at y, not y prime, but the actual y itself, the function itself of -3, and see what that equals. That's going to be for my max, and that is going to be equal to, let's see, -3 to the third power, plus 3 times -3 squared. Again, I'm going to my original function, my original y, minus 9 times -3 plus 5, and that equals -27 plus 27 plus 27 plus 5, that equals 32. Max is actually -3 comma 32. So it's actually pretty high up there. It's really higher than 5. It's actually way high up there. Now for the point of inflection, so this is for the max. So the max is -3 comma 32. Now for the point of inflection, I'm going to take -1 and put that into the function. So y of -1 is equal to -1 to the third plus 3 times -1 squared minus 9 times -1 plus 5, and that's going to be equal to -1 plus 3 plus 9 plus 5, and that is 16. So my point of inflection is going to be -1 comma 16. And so actually the max and the point of inflection are actually pretty high up. Little rough sketch, you don't see it so much like that. But let's look at Desmos. Let's get a little bit more accurate. Hopefully it'll be pretty much similar to ours. And let's do that right now. We are in Desmos. And we're going to look at, I'm putting in the original function y equals x to the third plus 3x squared minus 9x and then plus 5. And as you can see, whoa, this is pretty good. So that's -5, 0. That's 1, 0, just like we thought. That should be 0, 5, just like we thought. And let's go down a little bit. Oh, I lost all those points in it there. And I'm going to shrink this a little bit so we could get up to, so we can see up to 32. Again, that's is all points. That's the points I figured out. And this point is -32. Yeah, Desmos won't exactly. Let's see. -1 is around there somewhere. Best way I could, if you want to find the point, if you want to actually find the point of inflection, best. I'm just gonna type in y equals 16. Y equals 16, and you'll see that it intersects at x equals 1. So that's the point of inflection. I just want to show that -116 is on my graph. That's the max. That's the min. That's the y-intercept. That's the x-intercept. And other than that, it's pretty much, it looks pretty much like we, well done. It looks pretty much like we said it would be. So there you go. Okay, everybody, that's this example. Let's see if we could do another nice example. Okay, we're gonna go through step 1. We want to sketch this curve here. So the domain equals all is -infinity to +infinity, and the range. Now the range is not going to be. It's going to, since it's a 4th degree polynomial, it's going to have a certain minimum point, and then Fourth degree equations usually they either look like that or they look like that or something, something like that. So we'll have to check that out exactly. So for the range, it's going to be it's going to have a bottom, which I don't know what it is yet. Then it's going to go up to infinity. I'm not gonna waste my time getting the bottom now because we're gonna get that anyway. Um, let's go. I think it's just easier that way. Let's go now to the next step, which is the intercepts. So the y-intercept, again, that's the easy one. Y-intercept is just going to be 0 minus 0 plus 0 minus 0, which is 0. So the y-intercept is going to be 0 comma 0. But guess what? The x-intercept is going to be the same thing. Because if I factor this, y equals x times x to the third minus 12x squared plus 48 minus 64. But there's an x over there, so x is a 0. So x-intercept is x equals 0. Let's see if there's more. Well, this is I'm going to say the coefficient denied it up to 0, so I can't. Let's just try. I'm going to try 4. It could be any positive or negative factor of 64. I'm going to try 4. Actually, I tried a whole bunch of them. 4 was the one that actually got to work. So I don't want to waste time going through a million trials and errors. Let's just get to the one that actually works in this video. Number 1, negative 12, 48, and negative 64. And we got 1, 4, negative 8, negative 32, 16, 16. 4 times 16 is 64, and my remainder is 0. So that means that y is equal to, so far, x times x minus 4 times x squared minus 8x plus 16. This is a quadratic. This I could just see. One y equation for y. And let's that means that my x-intercepts are going to be the x-intercepts are going to be 0 and 4, and they're both going to go to the both odd exponents, so they both go through. Which means that roughly, very roughly, function is going to come down here. And that's going to be 4, and that's going to be 0. And I'm not sure now. It might have more squiggles down under here or anywhere, but this is what I have at this point. I'm just drawing what because at each stage the graph is more developed. Okay, let's go to step 3. Step 3 is the asymptotes, and again, there are for a polynomial has no horizontal and no vertical. No horizontal asymptote, no vertical asymptote. Okay, now we're going to look at we're going to go to step 4. So we're going to look at where this function is increasing, decreasing, where it has maxes and mins and so forth. And don't forget that when I get the min, I'm going to have to put that number in here as my range, because I did leave that blank. I didn't forget that. I want to say something. I didn't say anything. I was just gonna say with the fourth polynomial, the absolute min is going to be a local. Well, but let's bear that out with some calculus. I'm going to go now to step 4. Okay, well, for step 4, we look at the first derivative, and y prime. Now, just to remind us, the original function was x to the 4th minus 12x cubed plus 48x squared minus 64x. And the derivative of that is going to be 4x cubed minus 36x squared plus 96x minus 64. Notice I can factor a 4 out of everything. This equals 4 times x cubed minus 9x squared plus, let's see, 24x minus, I'm going to say 16. And let's see about factoring this guy. 24. If I plug in x equals 1, I get 25 minus 25. 1. Yeah, if x equals, so the coefficient 1 minus 9 plus 24 minus 16 is 0. So I'm going to do synthetic division with x equals 1. So 1, negative 9, 24, negative 16 is my remainder. Bring down the 1, 1, negative 8, 16, 16, and 0. Oh, and this is, so y prime is going to equal 4 times x minus 1 times x squared minus 8x plus 16, which is, so y prime is equal to 4 times x minus 1 times x minus 4 squared. And again, I just factored that quadratic. Well, that means it's going to go, it's going to go through at x equals 1, and it's going to bounce. So here it's going to go through, and here it's going to bounce. So I'm sorry. I take it back. I had a mental lapse for a second. Let's just forget that. It actually the truth is, well, we'll see. It actually just gonna that's kind of gonna happen, but not the way I meant. I was referring to the bouncing. I was referring to the original function, I think from algebra. I just had a quick little mental lapse, but something like that, something analogous that actually is going to happen. But let's not get ahead of ourselves. So our critical numbers. So y prime is so the critical numbers are 1 and 4. And now let's take a y prime graph. So in a section of 1 and 4. So our test numbers are going to be 0. Let's make 2. And let's make 5 test number. And so for 0, I have negative 64, because it's just basically that negative 64 right there, which is negative. So the function is decreasing. When it hits 1, at 2, I'm going to get, well, y prime is equal to 4 times 2 minus 1 times 2 minus 4 squared, which is 4 times negative 2 squared, which is 16, which is a positive number. And when x equals 5, I get 4 times 5 minus 1 times 5 minus 4, which is just positive 16, which is also positive. So notice in a way it was a through. I wrote through and bounce, and then I crossed it out, but in a way it was a through and a bounce, in the sense that this is this is a not max min. This is not a max, nor is it a min. But this guy here, since it goes negative and it becomes positive, this is a min. So x equals 1 is actually going to be our min. It's actually going to also wind up being our absolute min. So let's put x equals 1. Let's see what happens when I put x equals 1. I want to pause for a second and go back to that thing I left out. And because again, how am I so confident here? Because I know it comes down, bottoms out at x equals 1, and then does nothing but increase. So let me just go back here. I know that when x equals 1, that's my min. That's my local min, but it's also going to be an absolute min. So let's just have a second here to. Remember, I was supposed to fill in that number. Let's just do that right now. So y of 1. This is going to give us our bottom of our range. Y of 1 is equal to 1 minus 12 plus 48 minus 64. Which is, let's see, that's 49 minus 76. That's going to be 76 minus 49. That's a 6, and that's 1. That's 7. So that number there is 27. Our absolute low point is going to be 27. We take our second derivative and we just do the regular process. We get y double prime is equal to 12 times x squared minus 6x plus 8, which equals 12 times, let's see, x minus 2 times x minus 4. So the zeros of y double prime are 2 and 4. So we're going to see if we're going to see, are these points of inflection or not? Let's figure it out. So we're going to go, we're going to make a number line for y double prime. I'm going to put 2 there. We're going to put 4 over there. So we're going to test out 3 and 5. And let's just test out on 0, like 0. Well, when you test out 0, that's the same thing. That's just that last number. So that's positive. Y double prime of 0 is positive. Now let's try 3. So for 3, I have 12 times 3 minus 2 times 3 minus 4, which is negative 12, which is negative. So this is a point of inflection because it changes concavity. It goes from concave up to concave down. So 2 is a point of inflection. Let me make this. And for 5, I have, let's see, 12 times 5 minus 2 times 5 minus 4, which is 36, which is, again, is positive. I also have another point of inflection. That's very nice. Also, we got here 2 points of inflection, which is very lovely. So making a rough graph, our function is, we see from the y prime, the function is decreasing until I hit x equals 1. It's increasing everywhere after that. But as a little point of inflection, it's concave up this whole way. And then here it becomes concave down. And then here it becomes concave up again. Even though it's rising, see, it's rising, but it's concave down. And now it's rising, it's concave up. So just because something is concave down doesn't mean it's decreasing. It could still be increasing. So this is a rough draft of our graph. Let's do it on Desmos. Let's go over to Desmos. I'm going to switch projectors here. And let's share the screen. And let's Desmos. Okay, so we don't need this anymore. Let's see, so original function was x to the fourth, x to the fourth minus 12x cubed plus 48 squared, and then minus 64x. There's no, and I'm gonna have to well, let's see, I'll have to. Oh, that's good. So this is gonna go. See, so it's hard to even see the graph here. So, see if you notice, it's not quite. It's very close to the y-axis here, but it's not actually. It doesn't actually touch the y-axis until. Doesn't actually touch the y-axis until that point right there. 0 point. That's the only point that actually touches the y-axis. And oh, I gotta go one more. Sorry. That's point inflection. And again, Desmos doesn't really show you points of inflection, but there is a point of inflection when x equals 1 and y equals negative 27. Let's just oh, you know, I'm just gonna put in a point 1 comma negative. That's what I should have done before. Oh, I'm sorry. Beg your pardon. 2 comma. That's right. 2. There you go. And that's a point of inflection right there. And that's the point of inflection, and it's also the X-intercept. That's the X-intercept and a Y-intercept, and that's the local and absolute min, and that is our graph. Okay, everyone. I'm going to do more examples, and I'm going to make a third part to this video. I want to do a lot of examples, so I'm going to do some more examples in part 3. So see you guys next time. Bye, everybody. Bye. It's been loads of fun.